I'm with STEM Success Center, and today I will be doing an example in optimization. Today's example is going to be needing to enclose a rectangular field with a fence. We have 500 feet of fencing material, and a building is on one side of the field, so we won't need any fencing for where the building is. And essentially, the question is, we want to determine the dimensions of the field that will enclose the largest area. So like in most optimization problems, we need to first probably draw a sketch that'll help us with finding like the two formulas that we're going to need to either maximize or minimize a problem. So first off, we know that we're trying to maximize a rectangular field. So just a quick sketch. This could be the possible fence. We'll say this is our building, and this is, so we need this side, which we'll say it's X, and we'll say this is Y. And since what we're trying to do essentially is we're trying to use at most 500 feet of fencing material. So for the largest area. So in this case, what we want to do to maximize, since this is a rectangle, we are trying to maximize on an area X times Y. And then, given this, our constraint is going to be 500 feet of fencing material. Knowing that, we only need fencing material on X, and then X and Y. However, we don't need any fencing material on the building. So what we're going to say is it's going to be the fencing that would take this side, which would be X, plus the fencing that would be needed for this Y, plus the fencing that would be needed for this side, which is also coincidentally Y, which is just X plus 2Y. So to make this simple, because right now we actually have two variables in both of our functions. So what we want to do is we want to solve for one variable. Today we're going to pick that to be X. So if you need to pause, write that down real quick. Try to get my shadow out of it. Cool? Solid. So let's solve for the constraint for X. Just to make sure we have that actually maximize, it's going to be A equals 2, not 2, X times Y, and constraint, it's going to be 500 equals X plus 2Y. And so what we want to do is we want to solve for X on the constraint. So what we can say is 500 equals X plus 2Y. And what we can do is we can minus 2Y from both sides of the equation. And this gives us 500 minus 2Y equals X. And so given that, we can actually substitute this in to the area function. So we know that area, we'll say it's a variable Y, is equal to 500 minus 2Y times Y. So you'll notice that went from X times Y to 500 minus 2Y. So this X is actually right there. Good. So now that we know that, we actually want to make sure that we can solve on a closed interval. And so the way we can go about doing that is actually setting AY equal to 0. And so what this means is 0 equals 500 minus 2Y times Y. This actually just comes out to 0 equals 500 minus 2Y, which is then Y equals 250, and y equals 0. And this y equaling 0, and then this equaling 250. So essentially what we're saying is that we have an area given this function on interval 0 to 250. So that just means that our fence can only be 0, which means no fence, or 250, in which if you were to draw it out, it would just be a straight line, essentially. And that's not exactly the best use of our fence to maximize area. So what we want to do is we want to find the critical points. And to find critical points, we just take the derivative of our given area function, which is simply going to be area prime, which is equal to, now an easy way to make this a bit easier would be if we just multiply it out, 500y minus 2y squared, otherwise you'd be using the product rule, and then area prime y would equal 500 minus 2y or y. Solid? And then to find that critical point, we would set this equal to 0. So it'd be 0 equals 500 minus 4y, which is really just negative 500 equal to negative 4y, which is then just y equals 125. And that is one of our critical points. And essentially what this means is that when y equals 125, that's going to give us our maximum area. And so to find out what our maximum area would be, we would simply plug it back into our area function. So it would be a area of 125. And this would give us 500 minus 2 times 125 times 125. We're just gonna cool. And this would actually give us 31,250 feet squared. That would be the maximum area. However, what our problem really wants is the dimensions that we would get 31,250 feet squared. And the way to find that out is actually just plugging back in our y, which was 125, back into our constraint. So our constraint was 500 equals x plus 2, and we can just plug in 125, and that gives us 500 equals x plus 250, because 2 times 125 is 250, and then 250 equals x. And so what we can say is the dimensions that yield our largest area would be when x is equal to 250 and y is equal to 125. And that's about it.